All right, chapter 2 talks about chemistry of life in terms of just some basic chemistry concepts, and then moving on into the molecules that make humans up, that make up all of life. And there's going to be 4 basic groups of those molecules. And so chapter 2 looks at chemistry, and in some cases this is going to be kind of scary to some students because chemistry can be very difficult. It is its own field of science, and when we start talking about atoms, elements, molecules, then people start to get scared. All right, but unfortunately, we can't understand biology without bringing chemistry into it. It's very important. So I prefer the field of biology, all right, and I sometimes want to avoid the topic of chemistry, but you can't study biology without having some chemistry intermingled into it. So as we go through chapter 2, I'm not going to spend a whole lot of time on the chemistry component, but rather what you need to know are just some of the basic definitions and core understandings of chemistry. At the end of chapter 2, or in the middle really, that's when we start talking about the macromolecules. All right, the nucleic acids, the proteins, the lipids, fats, and carbohydrates. And all of those you've probably heard before, but hopefully through this chapter and then throughout the course, you'll have a better understanding of what those are. And as far as the lecture notes go, I won't spend a whole lot of time on the audio portion of that because you have the notes section of your PowerPoints, and then there's a pretty good 10-minute video that just focuses on those macromolecules. All right, so points to ponder for this chapter, and you can look at this as well as look at your chapter 2 objectives that are already posted for you. All right, how are living things organized from atoms to molecules? All right, what is pH? How does it impact you as a living organism? The 4 macromolecules, what are those? What are the structure or subunits and function of those 4 macromolecules? So you'll want to be able to just list those: the nucleic acid, the proteins, the lipids, and then the carbohydrates. But you're also going to want to have a broader foundational understanding of what those molecules look like and what they do. All right, proteins specifically, very well organized, and you have to understand that their shape, right, their actual 3D shape is very important to their function. And then there's, within nucleic acid, 2 types of nucleic acids, the DNA and the RNA. They are similar and yet very different, so you'll want to know those differences as well. All right, so building blocks from large to small, you have matter. Everything around us is composed of matter, from the air we breathe to the chair we sit in, the ground we stand on, our own body. All right, we are composed of compounds, composed of molecules that are composed of elements. All right, elements are the basic building blocks of matter, and those cannot be broken down any further. All right. Atoms are the smallest unit of an element that retain the element's physical and chemical properties. When atoms bond together, those form molecules. All right, now here we have the periodic table, or a portion of the periodic table actually. Gives you an idea of how elements are going to be organized. Right here you have hydrogen. Its atomic number is 1. Its atomic symbol is H. Its atomic mass is 1. And you skip over here, now you have helium. Atomic number 2, atomic mass of 4. And these are all going to be organized in a particular way according to the mass and the atomic number. The periodic table shows you the atomic symbol. We'll look at carbon, That's a very basic one. The atomic mass is 12, and then the atomic number is 6. The atomic mass is the number of protons and neutrons of the element. An element can be referred to as an atom. Each atom is going to be composed of 3 different subatomic elements, the neutron, proton, and electron. Each component is defined by the location relative to the nucleus and to the charge. Atomic number will always stay the same, whereas the atomic weight will change with gravity. Just like on the Earth and the Moon, a person's mass is the same, but the weight can be very different due to the differences in gravity. The atomic number will not change between the Earth and the Moon. Here you have the 4 basic subatomic component particle of the atom, and so you'll want to look at these and memorize them. All right, just in case there are a couple of questions on the quiz or the exam. All right, now I mentioned location, and the location is very important in terms of having the nucleus here. That's where you'll find the proton, and then the electrons are going to orbit outside of that, the nucleus, and they're going to stay in those orbit. They're always going to be moving, and you have the number of protons, the number of neutrons. 6 is going to be the constant number, and as long as the protons and the neutrons are the same, then your charge is neutral. All right, 7 protons, 7 neutrons for nitrogen, charge is neutral. 8 and 8 for oxygen is a neutral atom as well. All right, so isotopes. Isotopes are atoms that have the same atomic number but a different atomic mass, because the number of neutrons differs, and so therefore the charge is going to be different. Isotopes are unstable due to the unstable nature of the configuration or the location of the atoms, the components of the atom. Depending on the isotope, the amount of radiation emitted can differ substantially, and the damage to a person can be very different as well. All right, radioisotopes are useful in dating old objects. They are used to image body organs and tissue through X-rays. They can also be used to kill cancer cells. So if you have radiation therapy, you're using elements that are classified as radioisotopes. They are not stable. All right, radiation can be harmful by damaging cells and DNA, and that can lead to cancer. So it's interesting how radioisotopes are used to kill cancer cells, even though radiation is harmful. All right, so that radiation therapy has to be very specific in targeting the cancer cells, or it has to be very well monitored by the physicians to make sure that you're not causing additional damage to the healthy cells when trying to kill out the cancer cells. All right, a radioactive isotope will behave the same way in a certain setting as the normal atom. And the big example, the easiest example, is going to be iodine. Iodine, when consumed by a human, will move directly to the thyroid. The behavior will be the same whether it is normal or a radioactive isoform. And just as an example, we'll look at the thyroid here. The thyroid sits on top of the larynx above the trachea, and it's a butterfly-shaped organ. And if you're having problems with your thyroid, which we'll talk about later in the semester, a good way to look at it is to have a person ingest radioactive iodine, and that iodine, after a few hours, will go directly to the thyroid. And then you can go back the next day and take a picture, a scan of that person's neck, and you can have a picture of the radioactive material. So I needed to have a thyroid scan done, I don't know, 15 years ago. And to do this, I took a small amount of radioactive iodine solution. And at the time, I was working in a research lab that used radioactivity. And after I drank this radioactive solution, I went back to my lab and I took the Geiger counter, which is just a handheld apparatus that can be used to identify radioactivity. You may have seen this on the news. And I put it up to my thyroid, and there was no clicking sound. And then I moved it to my stomach, and it just went off the chart because that radioactive iodine that I had just drank was still in my stomach. All right, then the next day I came back. There was nothing in my stomach, but it had all tracked to my thyroid, and that's where the clicking sound was when I held up the detector end of the Geiger counter. And then that day or the next day, I went back to the doctor's office and I had this scan done. And what they're showing here is that in this patient, right, there's a missing portion of the organ. So maybe their thyroid is not working enough, and they're missing this part of that butterfly-shaped organ. All right, scans can be done on the brain as well. And that's the idea of isotopes. All right, molecules made of atoms that are bonded together. They can be the same atom or they can be different atoms. And a lot of times, molecules are going to be created by ionic bonds. So atoms in this type of bond donate or take on electrons. So if you remember, those electrons orbit the nucleus, and sometimes those atoms can move over to the next atom in the process of an ionic bond. All right, so you see a picture of it here where you have sodium, you have all of its electrons, and you have chlorine, and you have all of those electrons. And you mix them together, and this sodium atom goes over to chlorine, and you have a compound or a molecule that is made now of sodium chloride. All right, now covalent bonds, so ionic, you're giving up. Covalent bonds are where you're going to share electrons. All right, so here, oxygen and water, you've got the outside electrons. All right, these electrons are going to be shared. And so in this case, one electron in each hydrogen atom. And now it comes over with water. This is a fully stable molecule, but the purple represents basically a half. So the hydrogen has 2 half electrons, which is equivalent to 1 whole one, just like here, and so it's stable. And likewise with the oxygen, it's sharing 4, which is equivalent to 2 that it had over here. So those are covalent bonds where you are sharing the electrons. All right, this is a ionic versus covalent bonding video. You should be able to find this in the McGraw-Hill, in the Connect material. Maybe it's a link within your ebook. If not, I will try to find this because I don't think it's going to work in the PowerPoint slide. All right, so now further into this lecture, we're going to talk about properties of water. All right, it can be liquid, it can be gas, it can be solid, depending on the temperature. And you're going to utilize hydrogen bonds as well as the covalent bonds. Right, hydrogen bonds are very weak. Hydrogen bonds are going to be very useful when we talk about DNA. There's a lot of hydrogen bonds within DNA. Right, the last thing that we're going to talk about real fast before I cut it off and you move on to the macromolecule video are acids and bases. Right, you all are probably familiar with it, but acids are going to be substances that release hydrogen ions, so they have more hydrogen. Bases have OH, or hydroxide ions.